Hermitian meet adjoint, adjoint meet Hermitian. In this video, we will discuss some useful properties of the Hermitian operators and prove some of their identities. Here we have from part A that we wish to find the Hermitian conjugates of x, I, and the differential operator d by dx. What is a Hermitian conjugate? Well, we know the definition of Hermitian operator, where we can switch operating on G to operating on F, so long as we're in the Hilbert space. Of course, we've seen that this entire section. The adjoint operator says that in order to switch, we have to take the operator from the G and to put it onto the operator to operate on F, we need to have the complex conjugate transpose. That's what that dagger symbol represents. So you put these two together, we get the Hermitian adjoint or the Hermitian conjugate, which just tells us that the operator operating on G is equivalent to the operator operating on F, and insofar as their relative position, due to these definitions joining together. And, I think the d by dx case will be really illuminating for this reason. And then here in part B, we wish to now showcase some of these definitions where we have the product of operators with the adjoint is equal to their inverted relationships, each of their adjoints multiplied together. So product adjoints is the adjoint to products. That's what we're trying to prove. Order here does matter, so be aware of that. Sum of the operators is equal to the sum of the adjoints. All right. And then here we have a kind of similar situation in the first property, just with the scalar constant. Of course, C we need to assume is in the complex numbers. Again, not necessarily complex or imaginary, but needs to live in there. Or rather, it needs to live in the complex, although it might not be imaginary. And then here we just have construct a Hermitian conjugate of the raising operator from chapter 2. Pretty cool. All right, let's see how we can get started. So if we want the Hermitian conjugates of x, I, and the d by dx, you see that we have a variety of different operators here, and we need to show that we can find the Hermitian conjugates via the inner product definition again, which we have up here. So clearly, the left side goes to the star, and G goes to the this is the same. We don't have to worry about it. Nonetheless, if we plug in the definition of F and then with the inner product at xg, we see here that x doesn't really do anything. It's just a positional space. So we see that since it's real, we can easily just go ahead and put it into the conjugate side of things, and then push it back out via the definition. And by doing so, we realize that the adjoint or the Hermitian conjugate is itself. So we're cool there. We like that. We know that X and P are Hermitian. That was one of the big statements in quantum mechanics. But now we see, let's move on to the second case here where we have I. If we do the same thing, we see that in order to put it into the conjugation here, we need to take the conjugate of I, so that the double conjugate is the equivalence of I. And so here we just have a negative I there, proving that the dagger, which we know for a scalar is just a complex conjugate, is equal to negative I. Again, intuitively, we knew that. So here we get to prove it through a different lens, of course. Now, the derivative is not obvious at first, but a clever insight and use by integration by parts will switch the ordering from the derivative being on G to the derivative being on F. Let's take a look at how we do that. Of course, integration by parts is lovely. Here's the form. Integral u dv is equal to uv minus v du. This boundary term we're going to have to take some care of, which, as you see when we apply to our situation here, that cancels out. Why? Well, clearly the obvious candidates for this were u equal the function f and dv equal dg. All that stuff's easy enough. But since we're in the Hilbert space where f and g are living, we know that the necessity for being finite is what allows them to be in the Hilbert space. So at infinity, we know we got to go bye-bye, and that's what we see here, and that's why we cross this out. And of course, we've seen this before. We've seen this kind of terminology and, the wave functions have to go to 0 at infinity. That was all in the chapter 2 stuff that we were able to formalize by stating that the functions were in Hilbert space. So as you see, these don't normally happen, but the vector space that we choose gives us a little more freedom to interact with these calculus methods. All right, nonetheless, we see here that we're just multiplying in the integrand so we can move the order. We acquire a negative sign, and the negative sign is assumed into the operator itself. So when we distill it back to the inner product notation, we see that the negative sign attributes to the derivative. So interestingly enough, the Hermitian conjugate is the negative of the derivative. That's pretty cool. It's not necessarily obvious, but really cool to see come together. Now on to B, where we wish to prove some of the properties. And of course, here we're looking at, the product of operators, where the dagger here means that we need not only the complex conjugate, but the transpose. We cannot assume that operators are unidimensional. In fact, a lot of these will be represented by vectors and matrices. So by the definition, here we're taking the green product and we're just simply dumping it to the left side, where we have Q and R multiplied together still, but we still need the transpose conjugate. However, this is also done in parts thanks to linearity. And we see here that if we have Q and R as a product, R operates on G first. So to peel this off, we have to get Q to the other side, which is what we see here in the red. We take Q, take it over to the left-hand side. Now we just see that we have R operating on G still. So now we have to peel R off and put it right here. And we see here that we have two equivalent statements based on the initial definition that we started with the left-hand side. Let's see what we can conclude then. Since the both starting points were the same and the equal signs followed through, clearly equating them leads to the blue equaling the red, which is what we see here. And, this is great. This is good that it's equivalent. What we need to understand here is that the reverse ordering matters a lot. And, this should remind you of things that we saw in linear algebra and the properties therein. Things like the transpose of multiplication, we have to switch, and that's what we see here. Inverses, determinants, all those things matter on order and dimensionality. And so we need to factor that in order to address whatever operations we see that are not just scalar. In the scalar case, this doesn't matter. Clearly, the order will be what it is. But in the non-unidimensionals, we have a lot of other things to factor in. So linear algebra is poking its head out quite heavy. And if you're uncomfortable, the appendix in the book is cool. There's also plenty of great text out there. But, nonetheless, we have to get used to this kind of reasoning due to dimensionality. Big takeaway there. All right, so enough of me rambling. On to the second property. The sum of operators uses this linearity argument again. Recall linearity, where we can operate, move through. We discussed that last video too. But here we see that we are simply trying to distribute F and Q with G here, F, R, and G here. The minus sign comes from this. Of course, then now we can peel this off to the other side, which we see here. Peel R off to the other side, we see that here. And then we could rejoin them via linearity again, and we see that we get this thing. Of course, here the green and the red are what we see are equal, and so that's what we were able to prove, and we like that. All right, so we have here, moving on, and also note that you could use the same argument that we did with the blue and the red and the before. Take this to the other side, but we were tasked with finding this. Nonetheless, distribute, switch, combine. We've seen this before in chapter 2 with things like proving the linear combinations of solutions is a solution. So this should be at least familiar to you. All right. Anyways, moving on then, we see that, similarly to the first product of operators, we see that if we have a scalar constant, we just have the complex conjugate, no big deal. Being a scalar, it doesn't matter, it can be pushed outside. Again, linearity allows this, so we prove that without much hassle. Now, on to the last part. Let's go check it out. We see that we are revisiting something from Chapter 2 with the raising operator, which, if we recall, was defined as A with this plus sign here to let you know you're raising it. Don't be fooled, it's still an operator. Here, the constants, whatever. But what we're trying to point out is the fact that it's composed of I, momentum P, and a position X. If so, we see that if we want to find the Hermitian conjugate, we have to take the conjugate of the I, the P, and the X. Well, since we know that P and X are Hermitian, which we showed X earlier, X dagger X is X, P dagger P is P dagger is equal to P. Cool there, we like Hermitian. We also showed that the I was just simply the complex conjugate, so go ahead and plug them all in. Again, because P is Hermitian, we don't have to switch these. We showed that with the scalar or unidimensional being with property 3 of part B, that we can go ahead and just tidy this up as such. So no worries there. X stays X, P stays P. Just put the conjugate there and simplify. The two negatives cancel. So we see it nice and tidy there. But this is indeed the lowering operator. And now you see why the authors like using these operators in the Hermitian, conjugates and the linear algebra systems, because this taking the Hermitian conjugate of the raising gave us a lowering, and as you would expect, going the inverse is also true. The double Hermitian conjugate, or dagger-dagger, leads to the same result. Linear algebra is poking its head through in several places, so be aware and just enjoy the journey of this because it's going to be amazing. Thank you for watching, and until next time, stay curious, happy learning.